Hi, welcome to the talk about integrating a new physics engine into O3DE. So I'm Sergey, I'm a software engineer at AWS, Game Engine Developer Services, and I work on O3DE. And recently we had a chat with one of our Open3D Foundation members, and they mentioned they have their own internal physics engine, and they were like wondering how do you integrate that to O3DE? And I remember like going through steps you need to do, like what kind of how components will look like, stuff which I thought sort of a bit obvious, but actually then I realized it's not that obvious for people who are not familiar with the engine code base. So I decided to do this talk showing you a simple way how to get a physics engine running in O3DE. So the topics we're going to cover here, so we'll see how to like create a gem, what kind of code gets generated, what's its purpose, so how the component design will look like, and then we'll see how the actual simulation is going to work. And in the end, we'll cover a few performance-related topics that's quite critical for simulations. So we're not going to cover here things like asset pipeline or scripting or like editor workflows. These are very important areas, of course, but sort of our focus here is on the minimum set of steps required to get the simulation running. In this example, I'll be using an open source physics engine called Jolt, Jolt Physics. So it's under MIT license. You can check this link on GitHub. It has sort of a bit greater focus on parallelism, and that's why it was interesting for me as well to try it, to see stuff how it works on larger scale simulations, how it stuff compare to existing systems. Yeah, so first of all, so we need to create a gem, and we'll be using like O3DE script for that. You can also use Project Manager, but I did it through command line. So you'll use the commands like create gem with a gem path, and then enable gem in your project. Yeah, so after creating the gem, you need to sort of set up this build dependency on your third-party library. This will depend a lot on how your library is like structured, what kind of architecture it has, what kind of modules it might have. So I'm not sort of giving exact snippets for you, but just to mention a few examples. If the library is already kind of within a O3DE third-party system, then you can check like gems like PhysX or Blast, for an example, is actually pretty easy in that case. You can even just include like your library source code into the gem as well. This is something I actually did in my experiment here, some experimental purposes as well. And the other thing, you can use this feature from CMake called Fetch Content. So this allows you to download your library like directly from, for example, GitHub repo, and sort of build it as a part of your CMake process. So a good example for that is actually Recast Navigation Gem, which Oleg just mentioned in the previous talk. I can check that. So here's the projects which you get generated as part of the like gem generation. And I wanted to focus on a couple here. So one is the .api project. It's in the middle. So this is where the like public interface for your gem is going to be exposed. So other gems and your game code can depend just on this project. So, you know, you don't have to then like link your entire gem code in like dependent gems or your game code. And the .private object, this is where your implementation for the gem is going to live. So this is where you will keep like implementation for components, or private implementation details for a gem. And yeah, that's the point. So you can then like change, for example, your implementation code, and it won't either like statically link to other gems or cause them to rebuild. So that like saves quite a lot of build time. So here's an example of the API code which you get generated. So the request class is your kind of system interface for your gem. It will be implemented in the system component of your gem. So all this code is actually generated for you. So you don't need even to worry about it. The only thing you need to kind of think about is what kind of interface you want to expose in the request class. So in my example here, I'm exposing just one function called getPhysicsSystem. I'll show you where it's used later. Yeah, and the example how it can be, like, for example, accessed from the game code or other gems is you call your gem name interface, : get, and that's it. So you get a pointer and you can just call your interface functions on that. Right, so system component is effectively like a singleton for your gem. So all the global initialization which you need to do like once, you do them in the system component activation. It's sort of important to understand that this is run when the gem is loading, when like the system entity is activating. So for example, things like if you implement multiple game levels and you go from one game level to another, this will only be called once at the beginning. So this is really for sort of initializing global constants specific to a gem. Okay. Yeah. So so we'll have sort of, the further initialization code here, and the important bit here is the connecting to eBuses. So we connect to Joel Physics request bus. That's again to make sure the interface through the eBus works, and we connect to the TIG bus. This is something we'll need for simulation later. Yeah, so this is pretty much ready to do the simulation. The thing is, there's no much point in simulating nothing, like simulating empty worlds. So we need to put some rigid bodies into our physics world. And for that, we need to sort of find a way how to set up the data for them. And so in order to do that, we'll need to have a like rigid body component. And for the rigid body component, we also want to have a configuration structure that would like encapsulate all the data required for the Joel rigid body, in our case. So things like motion type, whether it's dynamic or static, things like mass, and if it's a trigger or sensor. Yeah, and we basically include this configuration in our editor rigid body component in this case. The structure kind of allows us to share this data then later between editor and game components, but you'll see how it works. Yeah, so once we have this structure, we will want to expose it to the edit context. So in the reflect method, so here the component has a reflect method. So in the reflect method, you set it to the edit context through the data element calls, which members you want to show in the editor. So all the kind of reflected members will then be visible in the component card, and users will be able to work with them through the editor. So without doing this, like without calling these data elements, basically nothing will be shown in the component card. So you will still have a component, but there will just be no data to edit in there. Yeah, the other sort of important thing is that this editor component, it only exists during edit time. So once you go to the game mode, this component basically doesn't exist anymore. And in order to make these properties available like in the game mode, we need to have a game version of this component. So that the game version of the component will actually construct the rigid bodies. Okay. Yeah, so this is how like the game version of that component will look like. It's basically the same name, just without the word editor. That's kind of common convention. I mean, technically it can be anything, but it's just convenient this way. And the game version of the component will also store the configuration, which we had in the editor component, and the rigid body ID, which we'll need for this kind of association between the actual rigid body and the entity. Okay. So the mechanism for transferring this data between components is through the serialization system. So in the reflect method, again, you specify by calling the field function, like which data you want to serialize. So if you don't specify this sort of field, nothing basically will be serialized. You'll just end up with component keeping like default values, effectively. So if you want to kind of save something, you need to do this reflection into serialized context. And the other important thing is this build game entity function on the editor component. So this is called when a game entity is built. And that process of sort of building game entities will ask each editor component, like, what do you want to do with the game entity? And our editor, Jolt editor rigid body component, basically it says that on the game entity, I want to construct a game time component, which is Jolt rigid body component, and pass the configuration into constructor of it. So again, if you don't do this line, basically your game entity will not have any rigid body component on it. You will have entities in the editor. You will be able to like edit those values, but then when you go to the game mode, nothing will happen in there. So this is something you need to kind of remember, how the data is transferred from editor component to game component. It's this build game entity mechanism. Right, so when the game time starts, the game component will activate. So this is where we will be like creating a shape from the geometry, and we get the entity transform here. We do it through get entity, get transform. And then we'll use this transform as an input for constructing the actual rigid body. So and the important bit here is that we associate this entity with the constructed rigid body by like setting the entity ID into the user data. Sorry. Yeah. Cool. Yeah. So this allows us basically to find out which entity that rigid body belongs to, and then we call the Jolt body interface function to create rigid body with that data and give us the ID. So the ID is needed to do the sort of reverse lookup. Is when you have an entity with rigid body component, and then you want to find which actual Jolt rigid body it belongs. It sort of has the association. So for example, later, if you want to expose additional public interface for your component, for example, to like apply forces or like get some information from the rigid body. This body ID will be used effectively to do the lookup to find the data. Yeah, so next, let's look at this simulation. So for the simulation, we'll be using AZ TIG bus. So the TIG bus requires us to implement one virtual function called onTIG. And a couple of important things about it is that it runs in the main thread. So you get this onTIG call in the main thread. And it means you sort of need to not block it for very long or not have like particularly long calculations there. Because main thread is also responsible for handling like OS events, like from the operating system. And if you end up like stalling the main thread for like more than like a couple of seconds, the operation systems, they don't really like that when they start like saying your process is not responding, it starts like graying out your window. And yeah, that's not sort of fun user experience. The other thing about the TIG bus is that it effectively tigs with the render frame rate, which means that the delta time which we receive, it can be variable. So sometimes it can be bigger and sometimes it can be smaller. This is something you need to accommodate for in your code. So it's not always the same delta time. It can actually vary. Yeah, through the get TIG order, you can just control sort of the order of how onTIG is called, like compared to other classes. Right, so yeah, so this is the implementation of the onTIG in our Jolt physics system component. There are basically two steps here. So one is to simulate the internal physics engine state. So this will not actually move kind of anything on the screen. It will only update the internal state, internal simulation state of the physics engine. And the next step after that, that's where we actually use the updated state to move entities. And like that will actually affect their position on the screen. Yeah, so this is the implementation of this simulate world function. So here we'll be using fixed time update. So like I said before, the delta time coming through TIG bus, it can vary, can sometimes be bigger, sometimes be smaller. And we want basically to use, normally for simulations, you use like exactly the same delta time. So this is to improve the stability of simulation, because like physics engines, they don't really like if you simulate them for like bigger time frames, because like things might start exploding there or like penetrating into each other. It also sort of makes simulation more deterministic. So if you need to, for example, replay it later, or if you use it in a networked game, for example, then determinism is important. Yeah, so we'll be sort of using it this way. The only thing to be aware of here is this sort of problem called well of despair, is when the longer delta time you receive, so the more physics updates you need to do to sort of fit it. And that itself makes this TIG longer than the previous. And then it means like the next time you receive on TIG, the delta time will be even bigger. And you end up kind of doing this physics simulation even more. So this can quickly degrade your performance to pretty much 0 frames per second. And the OS will not like it. So the kind of common solution here is to clamp delta time to some max value. So when you receive it, you just say, like, I'm only going to simulate like maximum of some max delta time. So like in PhysX gem, we use 100 milliseconds, but it will sort of depend on your on your needs. Yeah, so that's sort of about this fixed time step. Yeah, so the next step was to update the entity transform. So we updated now the internal physics state. Nothing has moved on the screen yet. Now we actually need to start moving our entities. So for that, we iterate through the bodies and we get their updated transform. We figure out from the user data which entity this rigid body belongs to. And then we call the transform bus set world TM. So that will actually set the transform of this entity. And that's what, for example, the rendering system will use then to figure out where it should render that object. Yeah, basically this is actually pretty much enough to do the simulation. And once you get the simulation running, like and giving you some observable result, it's unlikely you're gonna be simulating just like a couple of objects. So you're gonna be scaling, and you'll quickly end up having performance problems, like key problems in simulation. And for that, you may want to look at profiling. So apart from just using standard sampling profilers, you may also want to add some instrumentation to your code. And in O3DE, we have, for that we have this AZ profile macros. There are sort of a few of them. I'll just focus on a couple, I think, main ones. Is AZ profile function and AZ profile scope. So AZ profile function will measure the execution scope of this specific function, and we'll use the function name from the preprocessor. And the AZ profile scope, that's for measuring like local scopes, which could be sort of scopes within your function body, or it could be loop iterations, for example, like here. And we need to provide a name for the scope in that case. Yeah. So if you can see, this is how it looks in the PIX profiler. So you have our scope measurements called simulation steps. And then you can see bigger, there's a sort of full function name that was for the entire simulate world function. Also, you can use profiler gem. So that uses IMGUI rendering, which you access through like pressing home button. It works like in the editor, but also in the launcher. And the good thing about it is that it works also on platforms where PIX isn't available, for example, Linux. So here you kind of see similar information to PIX, where you see like the simulation step, that's our scope, and the entire function is the green bar. Yeah, so once you get done with the profiling, you might start looking at like parallelizing your simulation. So you can utilize these multiple CPU cores at the same time. And in order to use multi-threading, well, apart from you can just simply create your own threads, but the most standard 3D ways, there are two systems for that. It's the AZ test task graph and AZ job system. So the task graph is more preferable for short-running computational work that doesn't involve I/O. So things like simulation, for example, will be a good example for that. With the task graph, you have to sort of set up the graph explicitly up front. So for example, once it starts running, you can't keep adding new tasks into the graph. You can also sort of retain the graph and avoid dynamic memory allocations, like with jobs, where you sort of need to create a job, and then once it gets done, it gets deleted. The task graph has sort of a few number of features. So it's sort of more lightweight implementation. For example, it doesn't support cancellation. of jobs, but of tasks. But lots of lightweight implementation also gives a bit better performance. So here's the example how you use the task graph system. So you create a task graph object, then you add tasks as like existed functions or C++ lambdas. Then you create the task graph event and submit the task for processing. Then when you need to actually sync, like sync point, you call the wait function on the event, and basically that waits until all the tasks are completed. So in contrast to that, the AZ job system, so you would use it for longer running jobs, which might potentially run over even like multiple frames, like crunching some sort of large amounts of data. You'd use it for like IO heavy jobs. Although you sort of can build dependency graph with jobs as well, but you also have an option to like keep adding more jobs within the job function body. So you kind of have more sort of implicit dependency in this case. It has sort of a lot more features in that sense that it, for example, supports job cancellation, work stealing. This is sort of not something currently we have, but technically in the future, job system could run with lower priority execution. Because at the moment, we still have like lots of systems doing computational work in the job systems, which we haven't yet migrated to task graph. But technically, like if we move off all the computation stuff in the task graph, we could make job threads sort of run with a bit lower priority, which means the overall engine performance will be a bit better. So here's the, again, similar example to task graph, like how to use the job system. You create a job completion object, which is basically the same as a job, but just sort of doing nothing, just waiting for all the job it depends on to finish. Then you create the jobs to do your actual processing. You set the dependency to the job completion and call start. So that's it. After that, all those jobs, they start running. And then when you need to sync, your sync point, when you sort of need to make sure that everything's completed, you call this start and wait for completion on the job completion. Yeah. So let me quickly show you a demo. Just a second. So for that, I use duplicate. Ah, there you go. It's here. Ooh. So here we have like entities with box shape, which specify the geometry. We have a Joel rigid body component and a mesh, so we can see something on the screen. And we have like a bunch of boxes falling. Okay, so let me go back to. Oh no, I think I closed the presentation. Extend. Sorry, I think I closed the presentation. Just a second. And yeah, open the last slide. And yeah, so this is basically the end of the talk. The homework for you is to try to integrate a physics engine of your choice. There are plenty of open source ones. And let us know in the Discord group Seek Simulation how it worked for you. Regardless sort of outcome, we'll be happy to hear. So even if you fail, we'll be very interested to see where you failed, like where we might need to update maybe documentation or add comments or make API a bit more clear. So all of that is very interesting to us. So please reach out as Six Simulation Discord. My name is like Sergey P. Amazon, and here's a few links on documentation relevant to this talk. Cool, thank you. Well, that one is actually, oh, sorry. That one is actually using just the threads from the Jolt itself. The thing is, the Jolt has a quite sophisticated requirements to the threading system. Like you need to sort of have separate like barrier primitives. And I did make an implementation with job system, but it was crashing, so I sort of haven't figured out for the presentation purposes. But I think the task graph would definitely be preferable. So in my example, it basically just creates its own threads.
I didn't notice collisions between those cubes. So it looks like
they're
talk about one component, but it looks like you did a rigid body component and also a collider, or is it all embedded in one?
No, just one. So there's this box shape component, which provides the geometry, and you have Jolt rigid body component. Technically, we don't have to have collider components. It's not really, strictly speaking, required. So if you need them, like in PhysX, it sort of made a bit more sense. Here, the information sort of comes together at the time of constructing the rigid body. So it's sort of slightly different architecture. But I mean, strictly speaking, even in PhysX, you don't have to have collider. It was just our sort of conscious decision to do that type of design. It's not really required for physics.
It's interesting that integrating another physics system, like I was expecting that you would just take the components that already existed for doing collisions and kind of tie it to the backend, but you made the choice of going with different component structures. So I'm just kind of curious if you could talk about that.
Yeah. So this kind of bit separate types of approach. So you may want to do this kind of implement the API, which we have in AZ Framework Physics. But to be honest, that one itself is a bit questionable, whether we should do it. It's not particularly sort of physics specific, but it's just slightly sort of different approach because implementing that abstraction, you still have to pay cost for abstraction, so nothing comes for free. So there will be also overhead of using the API, and you might actually not want to pay for that overhead. So yeah, the question sort of about using the API or not for like additional physics engine is quite debatable, I would say. So
interesting is you can technically have both physics systems working at the same time. Just objects from one system would never interact with objects.
No, yeah, they will not. Yeah. But even if we implemented that API with another backend, they would still not collide because the different physics worlds. It's just whether you want to have interfaces work with both of those objects. But as I said, there is a cost associated with kind of the abstractions. So you may not know.
If you don't want to pay the cost, you can do a Python script that converts as close as possible physics components to Jolt back and forth, and then you can try natively both physics systems, with the same design.
Yeah, well, I mean, you see, it's kind of back to the question of having like generic common API. And when you have different physics engines, some things are common, but there's lots of stuff which is actually not that common. But when you use it, you often need a lot more than just minimum subset. So you then end up still having this dependency on the library. So if you look like, for example, multiplayer sample, although it uses physics gem, it still needs to do more than the API provides. So we still include actually physics SDK dependency there and use physics SDK directly.
Did you pick Jolt, let's say, instead of Bullet for any particular reason?
Yeah, I mentioned at the beginning is because it's sort of supposed to be more large scale friendly. So it was sort of interesting for me to experiment on that.
How long did it take you to integrate jokes into the particular joke gem itself? Like, how long was that process? Like, how many days?
To be honest, it wasn't, I mean, you can see there's not a lot of code here to write. I think most of the time for me was like either trying like different types of building this dependency with CMake, like to use it fetch content, or kind of things like that. I would say probably a couple of days overall. But like actually writing that code, I mean, it wasn't really that much.
If I may ask a question about the simulation itself, I'm a graphics artist, so I'm not ready to code, but is it possible to stop the physics simulation at any point and make that like a specific frame of the simulation to be back in the engine so that you can use the simulation maybe for any moving object to be baked in a certain position after a little bit of time?
You mean to roll back in time?
Yeah, for example, if you want the boxes just to be simulated on a surface, you make them fall, and then you want them to stay in position at a certain point after they fell on the ground and they stop moving. Can you do that?
Yeah, well, that comes from the physics engine itself. So once it's kind of fall down, it goes to sleep effectively. So it's more it has optimizations
So when you
inside
get
it.
back to the state, when you jump back to the viewport, you got the system that is essentially reset to the basic to the static position, to the first position, or to the last moment when you stop the simulation in place.
Oh no, when you stop the simulation, you go back to the edit mode where you don't, you have editor components. So you don't have anything in the physics world anymore. So in the physics world, you see we added RichBody in the game time component.
Okay.
And game time components only exist when you press Control-G or run the launcher.
That's clear.
So you see this kind of separation within edit time. That's what I was sort of trying to focus as well. So there is like editor time component, and there's game time. And